When you log into your account, you will enter the main page of TOffee. This is your dashboard that lists all of your simulations. It is split based on the physics you're modeling, so fluid mechanics, solid mechanics, and heat conduction jobs. We're going to set up a simple example for structural lattice-based topology optimization. We start by giving a name to a simulation, and we can choose the physics, so in this case, structural. When we create this will create a new item on our list, and by clicking on that, we enter the main page where we'll specify our problem. We start by uploading a geometry. We can see that on the viewer. This actually defines the design domain in which the solver will generate a structure. We can choose the material option. So in this case, we'll go for lattice. The solver will perform multiscale optimization in order to minimize the compliance of the generated structure. You can initialize the radii of the members of the lattice elements. A good starting guess can help you speed up the optimization. In the next menu, we're defining the boundary conditions. In this simple example, we have a cantilever beam fixed on one side and loaded with a 100 Newton vertical force on the other end. You can simply select surfaces. So we start with the fixed side. We click on the fixed side and specify the boundary condition to fixed. Similarly, for the loaded side, give it a name and select the surface. And can define surface load in vector form, so 0, 100, 0. In the next menu, we can define our volume constraints. So in this case, we will set a constraint to the entire design domain of 0.4. We could specify additional constraints, and we can have any number of custom subdomains and have different volume fractions in each of the subdomains. To define the mesh resolution, we'll use number of cells, and we'll specify the number of cells to 50,000. Finally, in the last menu, we can customize the number of cores that we use for the simulation, and we can also set the maximum number of iterations for this simulation. Okay, so now we have all our inputs filled in, and we can launch the job. This will create a dedicated machine for you on the cloud. It will generate the mesh, and then it will start running the multiscale optimization. You will be able to track the value of the objective function and the convergence of your problem while the solver is iterating to find a solution. The multiscale optimization has now converged, and you can visualize here a reconstructed result for our cantilever test case. As you can see, the lattice elements in regions of high stress have members with larger radii and thinner members in regions of lower stress. You can now download your final geometry along with more detailed outputs, including the displacement fields and the volume fraction field for your final result. This concludes our lattice-based topology optimization example.